Thank you very much. It's a pleasure for me to be here again. I was last year in the GYSS meeting, and always for me a great pleasure to be in Singapore and to talk to all the students who are here and the colleagues. So what I would like to describe today is how it's possible to use light for manipulating atoms. Manipulating means that polarizing, cooling, and trapping. What I would like to do is to show you how the basic conservation laws in atom-photon interaction can be used for controlling with light the various degrees of freedom of atoms. And I would like also, of course, to discuss the new perspectives which are opened by this method. There are, in fact, in atoms, two types of degrees of freedom. Internal degrees of freedom, which, for example, is the spin polarization or the internal energy, and external degrees of freedom, which are the position and the velocity of the whole atom, the center of mass. And I would like to describe two types of experiments. Experiment controlling the internal degrees of freedom by exchange of angular momentum between atoms and polarized photons. That's the subject of optical pumping. And second, the control of external degrees of freedom by exchange of linear momentum between atoms and photons, that's the laser cooling and trapping. Let me start first by reminding you that there are the wave-particle duality for light. Light is an electromagnetic wave with frequency nu, speed of propagation c, 300,000 kilometers per second. Light is also a beam of particles called photons, with energy h nu and momentum p equals h nu over c. And also, photons have an angular momentum depending on the polarization of light. And the elementary interaction processes between atoms and light are emission and absorption of photons, bringing the atom from an upper state to the lower state by emission, or from the lower state to the upper state by absorption. And of course, in such process, EB minus EM must be equal to h nu. This is just the conservation of energy. Of course, by measuring the light which is emitted, the frequency of the light which is emitted or absorbed by atoms, you can get information on the atom because, for example, if you take three different atoms, they have different spectra, different set of lines, which means that the spectrum of light emitted by or absorbed by an atom is some sort of a fingerprint of an atom. So by looking at the light emitted by a medium, the spectrum, you can identify what are the atoms which are in this medium. And also, you can also look at the light coming from the universe, and you get some information on the structure of the universe. But what I would like to emphasize in this lecture is that light is not only a source of information, it's also a tool for manipulating atoms. And that's easy to understand because when an atom absorbs a photon, it gains some properties of this photon, angular momentum, linear momentum, energy. So by choosing conveniently the light beam, you can prepare atoms in a given interesting states. And the first example is the absorption of polarized light can polarize atoms, achieve situation where all the magnetic moments of the atom are pointing in the same direction. You get a polarized system. And also laser cooling and trapping by using the pressure exerted by light on atoms, you can slow down this atom, cool them at the lowest temperature ever achieved. Okay, let me first discuss the transfer of angular momentum. In fact, atoms are like spinning tops. They rotate around themselves, and they have an angular momentum, internal angular momentum, g. And quantum mechanics tells us that the projection gz of g along the z-axis is quantized. It quantized, it means that gz is equal to an m h bar, where h bar is equal to h, the Planck constant divided by 2 pi, and where m is an integer or half integer, positive or negative, for example, 0, 1, 2, 3, or 1/2, 3/2, 5/2. That's the quantization of angular momentum, which is something basic in quantum mechanics. For example, let me take the simplest possible example of a momentum, an angular momentum 1/2, which means that an atom having an angular momentum 1/2, it can exist in two spin states, m equals plus 1/2 spin up, or m equals minus 1/2 spin down. So you have two possible values of the angular momentum. And at room temperature, if you have an ensemble of atoms with an angular momentum 1/2, these two states are equally populated, nearly equally populated. There's not too much difference of population. Now, what is important to realize is that light also has an angular momentum, and photons have an angular momentum, and this angular momentum depends on the polarization of light. If you take, for example, right circular polarization, the electric field rotates in the positive direction around the direction of propagation. GZ, the angular momentum of the photon, is equal to plus h bar. If sigma minus, left circular polarization, GZ is equal to minus h bar, and if you have a linear polarization, you have GZ equals 0. So by choosing the polarization of light, you can change the angular momentum of the photon which are absorbed. Now, let me describe now a very simple situation where you have a ground state of spin 1/2, angular momentum 1/2. So you have two spin states in the ground state, spin down and spin up, m equals minus 1/2 and m equals plus 1/2. And in the upper state also, suppose that the angular momentum in the upper state is 1/2. So you have two spin states, minus 1/2 and plus 1/2. Now suppose that you excite these atoms with the light beam having a sigma plus polarization. So the photon have an angular momentum plus h bar. So in the transition, the only possible transition where you absorb 1 unit of angular momentum is from minus 1/2 to plus 1/2. It's the only transition during which m varies by plus 1. In this case, m does not change, and in this case, m decreases by minus 1. So if you choose the polarization of light, you selectively determine what is the transition which is excited. So you excite selectively atoms from this state to this state. Once the atom in the upper state, it does not remain there forever. After a certain time, it falls back to the ground state by spontaneous emission of a photon, which can have any polarization. So it can come back in this way or in this way. If it falls back in minus 1/2, it can repeat the cycle. If the atom falls in plus 1/2, it remains there because there is no sigma plus transition starting from plus 1/2, because you have no state with plus 3/2 here, which would be excited by the polarization sigma plus. So you have some sort of a pump which pump atoms from this sublevel to put them in this sublevel. And this is why this is called optical pumping. You choose the selectivity of the excitation for transferring atoms from one sublevel to the other. And you put all the atoms in the plus 1/2 state, so you polarize the medium. And also, which is interesting in this scheme, is that if you look at the amount of absorbed light or emitted light, you see that the light can be absorbed only from this sublevel because there are no sigma plus transitions starting from here. So by monitoring the absorbed light, the amount of absorbed light or the amount of re-emitted light, you can measure the population of this sublevel. So you do two things with optical pumping. You pump the atom in this substate, and you detect optically any change of the two populations, which could be induced, for example, by collision or by magnetic resonance. You could make magnetic resonance transition between these two states, and you can detect them optically. And that's the optical pumping scheme for which Alfred Kastler got the Nobel Prize in 1936. And this scheme has a lot of fundamental and practical application. So at room temperature, in low magnetic field, you can achieve nearly 100% polarization. which would be impossible to get by ordinary method. And also, you can detect optically transition, which is very important because it's high sensitivity, because you detect optical photons which have an energy much higher than radio frequency photons. And of course, you can study non-equilibrium situation and look how the atom returns to thermal equilibrium by monitoring the amount of absorbed or emitted light. Let me just give you also a practical application, which was unexpected at the beginning, which is MRI, magnetic resonance imaging, using polarized helium atoms. You know, magnetic resonance imaging, it's a detection, very important scheme now for detecting, making an image of the density of protons in a living organism. You make magnetic resonance, and you detect the density of proton in the body, but of course you have to polarize the nuclei, the proton nuclei, so you have to put the patient in a very high magnetic field. In MRI, the patient is put inside the solenoid with a very high magnetic field. Now, if you have a patient breathing a gas of helium-3, which is polarized by optical pumping, so you don't need a big magnet for polarizing the nuclei. They are already polarized by optical pumping. And they fill the cavity of the lung, and then you see by MRI, you may take a picture of the cavity of the lung, whereas in a proton MRI, you see only the solid or liquid part of the body. And you can detect if some patient with asthma or smoker. So that's an example of application which was opened by optical pumping method and which was not expected at the beginning. So let me tell you also something else. You can control with light the position of the energy levels. That was, in fact, my PhD work. We demonstrated that a non-resonant light beam can displace the ground state of the atom by an amount which is called the light shift. And the important point is that the ground state is displaced by light by an amount, delta Eg, which is proportional to the light intensity. If you double the light intensity, you double the shift. And it has the same sign as the detuning between the laser frequency and the atomic frequency. If omega L is larger than omega A, the shift is positive. If omega L is smaller than omega A, the shift is negative. In general, two Zeeman sublevels have different light shift, depending on the polarization. So by exciting an atom with non-resonant light, you can change the frequency of the magnetic resonance transition between the two sublevels. And you know, there are two ways of considering light shifts. At the beginning, where they were observed for the first time, they were considered as a perturbation. Because if the light beam, which is used to optically pump the atom, displays the energy levels, then you introduce a change in the frequency you want to measure, the Zeeman frequency, and that's a perturbation. So if you want to make precise measurement, you have to make the measurement at different light intensity and extrapolate to zero intensity. But what is amusing is now light shifts have a positive aspect. They are opening new possibility to manipulate atoms, and I would like then after that to show you how. So I switch that, and I switch now to the second part of my talk, how to perturb atomic motion by light. If you take a very simple example of a target bombarded by a beam of particles, P, the particles bounce on the target, and as a result of this bouncing, the target is pushed. You have a transfer of momentum from the projectile to the target, and the target is pushed. The same thing happens if you replace the target by an atom and the projectile by photons, which are absorbed by the atom and remitted in all possible directions. It's exactly the same situation. And as a result of the transfer of momentum from the photons, which have a momentum, h nu over c, to the atom is pushed. And this, for example, is what happened for explaining the tails of the comet. The tails of the comet come from the force exerted by the solar light on the dust surrounding the astrophysical object, and it is pushed along the direction of the sun rays. Now, what is interesting is the orders of magnitude. The momentum of a photon is h nu over c. Now, when a photon is absorbed, this momentum is transferred to the atom, and this produces a velocity change, m delta v, which is m delta v equals h nu over c. And for optical frequency, you find easily that the velocity change of an atom absorbing a photon is typically on the order of 10 to the minus 2 meters per second, a centimeter per second. So it's very small velocity change. But once the atom is excited to the upper state by absorbing the photon, it falls back to the ground state after a time which is the lifetime of the excited state. And it can repeat the second cycle, and the third cycle, and fourth cycle. And since the lifetime is 10 minus 8 seconds, it can repeat the cycle 10 to the 8 times per second. So this small velocity change, which is 1 centimeter per second, can be multiplied by 10 to the 8 per second, and you get a velocity change per second, which is 10 to minus 2 times 10 to the 8, which is 10 to the 6 meters per second squared. And if you remember that the acceleration due to gravity is 10 meters per second squared, you find that the acceleration or the deceleration of an atom in a resonant laser beam is 10 to the 500,000 times bigger than the acceleration due to gravity. And this explains that if you start with an atomic beam with the initial velocity 10 to the 3 meters per second, and you excite with a counter-propagating laser beam resonance, then you can stop the atom in a time which is given by V0 divided by 810 milliseconds, and the atom travels over a distance of 0.5 meters. So if you have atoms moving with 1 kilometer per second, which is the case with ordinary atomic beam, you can stop the atom in 1 meter. And of course, there is a problem. When the atom starts to be decelerated, its velocity changes, of course. And because of the Doppler effect, if it was at resonance with the laser beam at the beginning, shortly after, it will be no longer of resonance because the Doppler effect will take the atom out of resonance. So you have to compensate. And the possibility for compensating is to have the atomic beam propagating in a tapered solenoid, producing a magnetic field changing in space. So you have the Zeeman effect, which changes the atomic frequency because an atom in a magnetic field has its frequency changed by the Zeeman effect. And you can calculate the profile in such a way that the change of the Zeeman of the atomic frequency due to the Zeeman effect compensates the change of the frequency due to the Doppler effect, due to the change of velocity of the atom. And in this case, you can maintain the resonant condition over the whole trajectory, and you get what is called tapered solenoid. And this picture shows you the exit of the solenoid here, and you see the atomic beam stopped here, and you get a cloud of atoms which are zero mean velocity. So you can stop an atomic beam with 1 kilometer per second. Now, slowing is not cooling. Slowing is you reduce the mean velocity. But in physics, the temperature is not related to the mean velocity. The temperature is related to the velocity dispersion around the mean value, the velocity spread. The bigger the velocity spread, the higher the temperature. If you want to have a very cold atom, you have to reduce the velocity spread. Now, let me describe you first the simplest cooling scheme, which uses the so-called laser Doppler cooling scheme. Suppose that instead of taking a single laser beam acting on atoms, you take 2 laser beams with the same intensity, the same frequency, detuned below the atomic frequency, nu L smaller than the atomic frequency. And they have the same intensity. If the atom is at rest, thus, here, there is no Doppler effect. The two radiation pressures are equal and opposite. They balance, and the net force is equal to 0. If the atom is moving to the right, the counterpropagating beam will have its velocity increased by the Doppler effect. And since nu L is smaller than nu A, this increase of velocity of the apparent laser frequency will get the atom closer to resonance. So for an atom moving to the right, the velocity, the force exerted by this beam will get closer to resonance, will be smaller than the force exerted by this beam, which gets farther from resonance. So once the atom is moving, because of the Doppler effect, the two forces will no longer be equal and opposite, and the net force will be opposite to the velocity. Okay, so you have a scheme giving you a force which is opposite to the velocity and which low enough velocity is linear in V. And you have a force minus alpha V, where alpha is the friction coefficient and the velocity is damped. And the scheme is called optical molasses. You achieve the situation, everything happens as if the atom was moving in a pot of honey. It is submitted to a force which is opposite to the velocity and proportional to the velocity. Now, you can make the theory of this effect, and you predict some equilibrium temperature you can get, and you can compare it to the measured value. Now, the question is, how can you measure the temperature? You cannot put a thermometer because you have a very dilute medium. So what is done is you make a time of flight method. You have the ball of cold atoms, which are the optical molasses, and you switch off the laser beam completely. So the atom will fall in the gravitational field, and they fall starting from their initial position and with the velocity, which is their initial velocity. And they will cross a probe laser beam below, which gives you a picture of the cloud of atoms following the switching off of the laser beam and falling down. And from this picture, you can measure the initial velocity distribution of the cloud, and you can measure the temperature. This is a time of flight method, and very precise. And when the experiments were done, it was found that the temperature was not, the observed temperature was not the temperature predicted theoretically. It was 100 times lower. So that means that there's something else in the physics, some other mechanism. And this is where light shift appears to be useful. And in fact, my colleague, Jean Dalibard, we identified what was happening in this molasses, and the following thing. Since you have two counterpropagating laser beams, you have a standing wave, and the intensity of the light is spatially modulated. And of course, the optical pumping also is spatially modulated. And the light shifts, which are proportional to the light intensity, are also spatially modulated. And you have a situation where the two ground state sublevels, spin up and spin down, are positions which are position dependent. And you have also optical pumping, which is modulated. And you have a situation where the two effects, light shift and optical pumping, are correlated in such a way that the atom is always climbing potential hill. It climbs the potential mountain here, and then it is pumped in the bottom of the valley here, and it climbs again, optically pumped here, and so on. So you have a situation which looks like the situation of the hero of the Greek mythology, Sisyphus, who was condemned to roll up a rock at the top of a mountain, and when he was at the top, he was put at the bottom, and they have to do the job again and again. And the same thing occurs here for the atom, but a combination of optical pumping and light shift, and that you can show that this leads to a very low temperature, about 1 microkelvin. There have been also other schemes which have been demonstrated from optical pumping experiment. I have no time to do it. I just give you some very simple scheme. Once the atom has been cooled by Sisyphus cooling, you can take the relay with another method, which is evaporation. If the atoms are in a trap, and if you have elastic collision between the trapped atoms, two atoms with energy E1 and E2 can collide, and you get a collision, E1 plus E2, E3 plus E4, and you have this one, this one. If E4 is larger than the depth of the trap, the atom with E4 leaves the trap, and the remaining atom has a very much lower energy, and by collision with the other one, the whole sample cools down. This is exactly when you blow above your cup of coffee, you evacuate the hot molecule, and the remaining molecule gets cooler. And with this scheme, you can reach now, currently, a temperature which is 10 to the minus 9 Kelvin, a billionth of a Kelvin. Compared, for example, to room temperature, we see 100 Kelvin, 300 Kelvin. So you see a big decrease of the temperature, and you have here temperature scale, where we have the sun, surface of the sun, the Earth, which is 300 Kelvin, the cosmic background radiation, which is 3 Kelvin, the cryogenic temperature by liquid helium and so on, which are a millikelvin, and now with evaporation and Sisyphus cooling, you get a nanokelvin. It is the laser cooling has allowed to reach the lowest temperature ever achieved. There is no other place in the world where you have such low temperature. And at room temperature, 300 Kelvin, the atoms of the air or the molecules move with a velocity of the order of 1 kilometer per second. Laser-cooled atoms have velocity which can be as small as 1 millimeter per second. So you have completely quiet down the temperature of the sample. You can also, with light shift, achieve traps for atoms, scheme for trapping atoms in a given region of space. If you take, for example, a laser beam which is focused and which is detuned to the red, the laser frequency is smaller than the atomic frequency, you remember that the light shift is negative and proportional to the light intensity. So the energy of the atom will be shifted down by the laser intensity, and the lowest value will be at the focus of the beam. So you will have some sort of potential well in which atoms can be trapped if they are cold enough. That's called a laser trap. You can also make something more funny. If you take a standing wave, you have a series of potential well and potential mountain. And if the light is detuned to the red, the atom will be trapped at the bottom of the potential well. They will be trapped at the minima of the standing wave. And you will have atoms trapped in a periodic structure which looks like eggs trapped in a box of eggs. And that's interesting because such a situation where you have trapped atoms in a periodic potential are similar to what happened in a solid where you have electrons trapped in the periodic potential produced by the ion of the crystal. And you have a system which simulates what happened in the crystal, and by looking at these trapped atoms, you can get some information, some news. For example, if you increase the size of the depth of the potential well by increasing the light beam, you can decrease the tunneling of atoms between potential well, and you can have really trapped atoms in the depth of the potential well. If you decrease the size of the potential well, then the atom can move from one potential well to the other by tunneling. And you have a transition between an insulator regime and a conducting regime. Something which is funny also, if you have a prism like that, and if you have an evanescent wave obtained by total reflection of a laser beam along this surface, you have an evanescent wave here with an intensity decreasing rapidly with the distance from the surface. And if the laser is detuned to the red, there will be a potential well. And if it is detuned to the blue, the light shift will be positive here and will be decreasing with the distance from the surface, and you will have a potential barrier like that as a function of the distance from the surface. And the atom coming like that will be reflected by this potential barrier, and it will bounce. So we'll have some sort of a mirror for atoms. And if you have a concave surface here, the atom will be moved like that. You will have a trampoline for atoms. And that will be interesting because that's a way of trapping atoms. So the last part of my talk will be, once you have obtained such laser-cooled atoms and trapping them, what can you do with that? What kind of application laser cooling and trapping opens? What are the new perspectives which are open? I think it can be understood very simply by two points. First, since atoms are very slow, you can observe them for a long time. And in physics, the measurement of atomic frequency becomes more and more precise when the time you take for measuring is longer and longer. There is a time-energy uncertainty relation, which means that with ultra-cold atoms, you can make very, very precise measurement. And you can make for example, more stable and more precise atomic clock, improving the GPS system. D'accord? Okay? First application. Second grand class of application, you know, of course, that Louis de Broglie showed that the basic feature of quantum mechanics, that with every particle is associated a wave, which is called the de Broglie wave, the wavelength of which is inversely proportional to the atomic velocity. The de Broglie wavelength is equal to h, the Planck constant, divided by mv, where m is the mass, and v is the velocity. If v is small, the de Broglie wavelength becomes larger and larger, and the de Broglie wavelength of ultra-cold atom can be very large, and the wave nature of atoms becomes easier to observe. And you can extend all the experiments which are done with light wave, interferometers, gradiometers, can be extended to atoms. You can make atomic gyromètres, gradiometers using matter waves. And second point, important point, is that when the de Broglie wavelengths become so large that the wave packets of different atoms in a gas overlap, they interfere, and you get a new state of matter, which was predicted by Einstein and Bose a long time ago, which is a Bose-Einstein condensation. All atoms, cold enough, condense in macroscopic quantum state, which is called a quantum gas, a gas which has properties which are typically quantum mechanical. And this is a field now which is extremely active, and which is a field of quantum gases. Let me show you how atomic clock can be improved by cold atoms. Let me first remind you what is the principle of an atomic clock. You have an oscillator, omega naught, which scans an atomic frequency. For example, the hyperfine transition of cesium atom into ground state. So you scan an atomic frequency. And with the servo mechanism here, you adjust the frequency of the oscillator to remain centered at the center of the atomic line. So you have an oscillator which is locked on an atomic frequency. Like a quartz, for example, a clock using quartz is locked to the vibration of the quartz. Here, you lock the clock to the frequency of an atom. And you see that this line has a width delta omega, which depends on the temperature. And this width becomes narrower and narrower when the atoms you are studying using are moving slower and slower. So by using cold atoms, you can improve considerably the precision of the clock because the frequency here is determined more and more precisely. And let me show you an example of what happens. Usual atomic clocks before the cold atoms we are using atomic beam, cesium atomic beam, crossing two cavities, separated by a distance L of the order of 1 meter. And in fact, if the two cavities are fed with currently with the same microwave source, you can show that the time of observation is the time it takes for the atom for going from here to here. You get that was found by Norman Ramsey, who found interference fringes, the width of which is determined by the time of flight between the two cavities. If you have, so the time of measurement is L divided by V, and it's about 5 milliseconds. If you have cold atoms, of course, you cannot use a slow atomic beam, because if the beam is too slow, the atom will fall into gravity. So instead of having a horizontal beam, you take a vertical beam, you throw the atom up, and the atom were slow here, they cross the cavity once on the way up and once on the way down. And the time between the way up and the way down is on the order of 0.5 seconds. So you increase the observation time by a factor 100. And this has been done in Paris by my colleague Christophe Salomon and André Clairon. That's called a fountain of cold atoms. It looks like a fountain of water where you replace the drop of water by atoms. And with this clock, you can get relative accuracy of 10 minus 16. And that means that an atom, a clock starting now, can keep an accuracy of 1 second over 300 million years. After 300 million years, it will be off by less than 1 second. And now we have also an optical transition, and you can reach 10 minus 17. So these clocks are such that if it was starting at the beginning of the universe, now, several billion years after, it will be off by less than 1 second. So with this clock, of course, you can also make such clock in space where you have no gravity, so the atoms are not falling. You can observe them for a long time. You can put them in the space station. And why it's important? It's because Einstein predicted in the theory of general relativity that two clocks in different gravitational fields do not oscillate at the same frequency. There is a shift proportional to the gravitational potential. So if you have a clock, a cold atom clock in the space station, and you compare the time that it gives with the time given by an Earth clock, then you can test general relativity with 2 or 3 orders of magnitude more precision than all tests which have been up to now achieved. So that's a very important issue, because it's always important in physics to check the theory. You can also make relativistic geodesy. You can make a map of the gravitational potential. And of course, you can look for possible variation in fundamental constants. So every time you have an increase in accuracy of measurement, you have a lot of application. And of course, you can improve the GPS system that everybody now uses. Let me now show you an example of application in interferometry. And an experiment, very fascinating, has been done by these Japanese colleagues. What they do, they take a cloud of cold atoms, of metastable laser-cooled neon atoms, and they switch off the trap, the atom fall, and pass a screen with 2 slits, and they arrive on a screen here. And since there are metastable atoms having a lot of internal energy, when they hit the screen, you get some important signal. So you can detect the arrival of atoms on the screen one by one. And what you observe is the following thing. It's a pity I have not the video, but you see a click here, a click here. Each atom gives a localized impact. So that means that atoms are particles. Each atom arrives at a given point in the screen, and this is detected by a signal. But if you accumulate the number of atoms, what you get? You see that the impact will be denser at the place where you have the predicted interference pattern given by a wave passing through the two slits, and whose wavelength is given by lambda de Broglie. So you see that's a very important, very simple experiment, very clear, give you the wave-particle duality. Atoms are at the same time particles and wave. Each atom gives the localized impact, it's a particle, and the spatial repartition of the impact is given by the wave which is associated by the atom. So each atom is also a wave. And the connection between the wave and the particle is of probabilistic nature. The wave function gives you the probability to find the particle in a given point. That's the basic postulate of quantum mechanics. And of course, you can generalize this experiment, make radiometers, interferometers, and you can repeat with de Broglie waves all the experiments done with electromagnetic waves and showing clearly that wave-particle duality exists not only for light, but also for matter. And the last point is Bose-Einstein condensation. And the idea is the following. If you have a gas here, and if you decrease the temperature, for high temperatures, the de Broglie wavelength is very small, and the wave packet associated with each atoms are completely separated. And you can think of this gas as a beam of particles, of classical particles. When you decrease the temperature, the wave packets start to have a spatial extent which is bigger and bigger. And at a low enough temperature, the wave packet will overlap. They will interfere. And the theory predicts that all the wave packets will condense in a single macroscopic wave function, which is called the Bose-Einstein condensate. So this transition from a classical regime to a pure quantum regime is achieved by lowering the temperature. That was not possible before because we didn't have any possibility to decrease the temperature in such a spectacular way. But now there are many, many groups in the world which have observed this phenomena. And you know, the first time it was observed, the Science magazine made an analogy between this state where all atoms are in the same quantum state, an army of soldiers marching in lockstep, with some soldiers which are not yet in the army, which are some atoms which are not yet condensed. Now, what is important here is that such a condensate is a pure quantum object. It's a gas which has pure quantum properties and which cannot be understood with classical mechanics. It exhibits properties like superconductivity, absence of friction, currents, which up to now were observed only in condensed matter. Now they can be observed in a dilute gas system. And in a dilute gas system, the interaction, atom-atom interaction, are more easy to detect and to observe and to measure, and you have a better understanding of the interaction processes. And in this Bose-Einstein condensate, you can make theory which are much precise what you can do in condensed matter, in solid-state physics or in liquid helium. And this is a new field which appears, which is quantum gases, and which is very, very important. So I think I can conclude now. I think that I hope to have convinced you that the better understanding of light-matter interaction has allowed several important advances in physics. First, invention. I didn't have time to explain that, but you know, something which has been extremely spectacular is that this better understanding has opened the way to the realization of new light sources, which are laser light. And laser light is something which is exceptional, which has properties of monochromaticity, intensity, directivity, which has completely transformed fundamental research. Because now in the lab, we have light sources which are extremely important. Laser cooling would not have been possible without laser. It's called laser cooling and laser trapping. With ordinary light source, you could not cool atoms to this extremely low temperature. So invention of new light source, invention of new scheme, optical pumping, laser cooling for manipulating atoms. You know, these advances are opening new research fields and allow us to ask new questions and to investigate new states of matter, like macroscopic quantum gases, which share many common features with light waves. The history of light, all over the time, shows us that basic research changed our vision of the world by introducing conceptual revolution, like relativity, like quantum mechanics, that completely changed our vision of the world, and also has led to an incredible number of spectacular applications. This, I think, shows that science is a fascinating adventure which should attract young students who want to explore new fields and find new solutions for improving our condition of living on Earth. So I think that we should all believe in the importance of science. And I would like to conclude by showing you a picture, showing in my personal case, I've been lucky enough to participate and to be present at some of these advances in optical pumping. I'll show you here a picture taken in December 1966, 1 week or 2 weeks after the announcement of the Nobel Prize of Kessler. It was in October 1966. And you see Kessler was here. He was a fantastic person, very open, giving fantastic lectures and able to excite young students to do research and to work with him. In fact, I did my PhD with him, and one of his colleagues here is Jean Brossel, and it was also, it was a pity that the Nobel Committee didn't give the prize to both of them, because nothing could have been done without the work of Brossel. And Kessler was very depressed that he got only himself the Nobel Prize without Brossel. But now the lab that they created is called the Laboratoire Kessler-Brossel. It takes the two names, and a lot of students are coming in this lab. And in fact, I was here in 1966, so more than 50 years ago, and it was about 3 years after my PhD. I did my PhD with Kessler and Brossel. And after the work for optical pumping, we progressively switched to laser cooling and trapping, and I got the Nobel Prize in 1997. And in this photo, you find here another person here, Serge Laroche, who was one of my first students, PhD students. And as you know, perhaps you know, Serge Laroche got the Nobel Prize in 2012. So you see that in this picture, in the same lab, the three generations, Alfred Kessler, myself, and Serge Laroche, showing that Kessler was able to create a family atmosphere, an enthusiasm for research, which led to the situation where 3 Nobel Prizes in the same lab, which is quite exceptional. And still continuing, a lot of people are here in the lab, and many interesting results have been obtained, and I think this is a very important thing, showing that to do research, you need to be in atmosphere, to find people who inspire you and who give you some motivation for doing research and also teaching, because teaching is something which is very important. Thank you very much for your attention.